Remember, all the questions in part 2 are worth a total of 2 points each. So here is the solution to 25. A couple things that I want to point out with this one. Make sure that when they tell you to use h of n as your y value, you don't change it to y, and that you also use an n over here. That's something that I see a lot of. Another thing that you want to keep in mind when you create functions is that you find the starting point and then find the pattern. The starting point is always our initial value, the 0 value for our x's. So we input a 0 and we got out a 1.5. Well, how did I get that? I followed my pattern of adding 1.5 because I tried to figure out, okay, how did I get from 3 to 4.5 to 6 to 7.5 to 9? And all I did was subtract 9 minus 7.5, 7.5 minus 6, and so on and so forth to get the opposite way. So if I work through my table this direction, I can go backwards and the sign will just be opposite. So I could add through the table and then backwards would be subtracting, or if I'm multiplying through the table, if I wanted to go backwards, it would be dividing. My starting point plus what's happening every single day, which is my n, I am adding 1.5 over and over and over again. And to show repeated addition, we show multiplication. That's why this is a linear function. Now, of course, we definitely want to check something. Anytime we create a function, we're not just going to move on. We want to make sure that this is correct. So I'm graphing it, and I'm noticing that I had to put in x in my calculator, but I want to make sure that the point, 0, 1.5 is there, 3, 4.56. So every single x and y value matches up to the table here, so we're in good shape. Question 26 was pretty straightforward. A couple of the things that you needed to have for this one: make sure all the points are plotted on your graph, pay attention to solid and dashed lines, and shading. So we can't just have like 1 or 2 points on the graph. You want to plot all of them. And the way that I did this was I solved for y, so I got y alone by moving the 2x to the other side, pulled my slope and y-intercept, and just graphed it. Now let's check it. I'm going to check it by graphing it, and I need to create a relation, and because I did some math to the original inequality, I am not going to mess around with that. I am going to graph the original one, the 2x plus y is greater than 1, and make sure that, yes, indeed, this works out to be true. Now, some people like to look at the table, but then you realize because this is a relation, your calculator yells at you. So the way that you can get around that to generate points is go to Menu, and then Trace, and we want to change our trace step first. Instead of automatic, change it to 1 and hit OK. After you do that, you can go into Menu, Trace, and graph trace. I think I pushed graph trace. Hopefully I did. If you use your left and right arrows, it tells you all the point values on the line for the inequality. One thing that I don't like about the inequality is that it's sometimes hard to see if it's a solid or dashed line, but if you hover your mouse over it, you can always check for that. But that's a big mistake that I see that happens sometimes with inequalities. So always be careful of solid and dashed lines. Remember, if it's greater than or less than, it's not equal to, so the line is dashed. And since it was y is greater than, we shade above. Question number 27, the first thing that you want to do is see if there's a pattern. I think that some people initially, and my mind always goes to this first, to see if there is an adding value every single time, because if there is, then we know it's linear, or subtracting for that matter. As long as it's a constant value that's being added every time, then we know that it's linear. So Rachel thinks it's linear and Mark thinks it's exponential. If you tried to prove Rachel right, you would have found that she was actually wrong. The number that you added every single time for the bacteria was not correct. So what I found was that there was actually a multiplier. So I divided, so how did I find that out? Well, I just did a quick check. I did 350 divided by 280. And I put a decimal in there so it would give me a decimal output. And then I just tried it again. So like 440 divided by 350 to see if I get a number that's close. And remember, this is real data, so it's about 1.3-ish. Oh wait, I did that wrong. 440 divided by, I was talking and typing, I shouldn't do that. divided by 350, again, is about 1.3-ish. So this is real life data, so we're not going to have the same number every time, and that's okay. But we want to say that the model, the better model, is an exponential function because we found that multiplier. Mark is right, and we chose this because of the multiplier, but you could also have said the graph is not growing at a constant rate. So that constant rate piece can also get you credit for this because it's not growing at a constant rate, therefore we could have eliminated the linear option, and obviously exponential was the only other option. So I decided to color code question 28 for you. You can see that we obviously start at 0, 0. If you're not going anywhere, the time hasn't passed, and vice versa. If the time hasn't passed, you haven't traveled anywhere, or in this case, the driver. So for 2 hours, 1 hour, 2 hours, she's traveling at 60 miles every hour, gets a flat tire for a half hour, so therefore her distance won't be changing. But then she decides to travel 30 miles, so her slope is going to actually decrease, so 30 miles every 1 hour. And notice how we end at 3.5 hours. In 29, there were a few ways to do this question. The easiest one, I think, was to graph it on your calculator and interpret the graph. So I graphed x squared minus 2x plus 5. Notice that it did not have any x-intercepts, so therefore it doesn't have any real solutions. Now, had I graphed it and it looked something like this, we would have said it had 2 real solutions because it had 2 x-intercepts. If I moved it to here and it, well, let's assume, I don't know how much closer I can get, this would just create 1 x-intercept if it were just touching at one point. So this is a little bit better. So I moved it down a little bit. You can see that it's just touching the x-axis once, therefore it'd have 1 real solution. But for the question that they gave us, it would not have any real solutions because no x-intercepts. In order to answer question number 30 correctly, we need to understand the structure of an exponential function. And again, we should know that this is an exponential function. Well, why is it an exponential? Well, because there's an exponent of a variable. And it's written in the form a times b to the x power, which is not really, so you don't really need to know that, but it should look something like this. So this is an exponential function. Again, why? Well, we're starting with a value of 5,100, and we are multiplying over and over and over again. Because when we show repeated multiplication, that's where the exponent comes into play. Unlike a linear equation, when we show repeated addition, we use multiplication to help us model that. So what is a percent change every year? Well, that is the multiplier, the 0.95, the base. So 0.95 is really 95%. And if you compare 95% to 100, you are going to realize that you are decreasing at a rate of 5%. So the important piece here is that you compare it to 100%. Always. You could also compare it to 1 whole, but I really like to work in the percents. I think it makes a little bit more sense to everyone when we do it this way. But obviously you could have also have done 1 minus 0.95 and gotten 0.05 and then converted that to a percent at the end. After reading 31, the first thing that I noticed was that this is a real-life scenario of a quadratic function. So what better way to model a real-life scenario than to graph it? So I graphed it, and it looks weird right now. Like if I look at this graph, it really looks to me like it's 2 lines, which we all know better than that. So the first thing that I'm going to do is look at my equation and realize the parabola is upside down, which makes sense. The toy rocket's being shot into the air. We're not shooting it underground and it's miraculously coming up through the ground after certain seconds, which would be kind of amazing, but not really realistic. So let's change our value up top here. Some of you, it might be a guessing game, so you might want to try 40. That's not high enough, so maybe we want to try 100. And what we're looking for is a U, and dun dun dun, here we have it. Oops, I tried to drag the wrong thing. There we go. So I'm looking at this. This is modeling my rocket. You can see the rocket starts on the ground, This is our y-intercept, or our x-intercept and y-intercept actually, and 4 seconds later it lands. We don't care about negative values because that would mean it would be going into the ground or back in time, neither of which makes sense in the context of this question. So the domain would be from 0 to 4. Make sure you use closed brackets, or you could write it in inequality notation saying that it would go from 0 is less than or equal to t is less than or equal to 4. And again, I should also point out the domain we should know is our x value. So we're only looking at the x-axis. And since I can't highlight on my graph on the calculator, I just sketched a graph from 0 to 4 for the domain. Moving on to question 32. My major caution on this one is if you are not making a table, you are probably making a mistake with the y-intercept. I can't tell you how many papers I've seen in the past that would be saying that t of d is equal to 30 plus 2d, because you assumed that day 1 was your y-intercept, which we cannot assume that. So you modeled your situation. Everything in my table I wrote in red first, and then I realized, oh man, they never gave me my y-intercept, so I had to work backwards to find it. There's other ways to come up with equations where you can use the 30, but I think that with what we've done all year long, find that y-intercept, that point, that initial point of 0, in this case 28. I followed my adding of 2 pattern backwards to get it. So here's my equation. T of 6, it didn't matter. We were just looking for the time, or in this case, what is it? The day, the 6th day. Here we go. It wasn't letting me scroll down, but now it's behaving. Okay, so I could either look at my table, I could continue my table all the way to 6, or you could have substituted in 6 into your equation up above. My recommendation is use the table because you know that the table is modeling your situation probably a little bit better, because if you used your equation and found out that I don't know, if you had done it backwards, what would you have gotten? Either 42 or 38. It would have been backwards. Just you would have been off by 2 if you had used the wrong y-intercept. You would have actually gotten, what, 42 minutes. So use your table or use your equation, but either way, I would verify it. I would make sure, because again, we are coming up with a function, so we want it to be modeled correctly. And I don't care what the graph looks like necessarily. I mean, I do, but I care more about the table. On the first day is 30, second day 32, and so on and so forth. It makes sense. If you had the wrong equation, those points would not have matched up to what modeled the situation.